Greetings, everyone. Welcome to a crash course on biostatistics, the conclusion. I'm Traci Marin, and I will be presenting this information to you today. Our agenda includes relative risk and odds ratio discussions, correlation and regression analysis, multiplicity issues, and lastly, survival analysis. We'll begin with relative risk and odds ratio. As some of you may already know, risk is used to define an outcome, and odds is used to define a precursor or antecedent. In a comparison between two groups, the terms commonly used are relative risk, or RR, and odds ratio, or OR. A greater understanding of ORs and RRs allows readers to draw more accurate interpretations of research findings. The ratio of risk of an outcome in a case group excuse me, when we're thinking of the ratio of risk of an outcome in a case group, we are comparing it to a control group. Relative risk greater than 1 usually implies that the exposed group has a higher probability of contracting a disease than the unexposed group. The relative risk less than 1 implies that the opposite is true, that the exposed group has a lower chance of contracting a disease than the unexposed group. And of course, the relative risk of 1 simply implies that the risk of disease is the same for both groups. So if we want to talk about it a little bit more deeply, relative risk can be defined as a ratio of the probability of obtaining a disease or an outcome among those exposed to something and probably obtaining a disease among those not exposed. Here's our common calculation for relative risk. Remember, relative risk is a population parameter that must be estimated based on sample data. We will be able to calculate confidence intervals for the relative risk, allowing inferences to be made concerning this population parameter based on the range of values within the RR, within the 1 minus alpha of 100% confidence interval. Keep in mind that the relative risk is often mistaken by some as the odds ratio, or with the odds ratio, an absolute risk. Relative risk is the ratio of the probability of an event occurring with an exposure versus the probability of the event occurring without the exposure. Therefore, to calculate the relative risk, we must know the exposure status of all individuals or subjects, either exposed or not, because we need those numbers for our calculation. This implies that the relative risk is only appropriate for cases where the exposure status and incidence of disease can be accurately determined, such as the prospective cohort study information. On the other hand, the odds ratio compares the odds of some event in an exposed group versus the odds in a non-exposed group, and is calculated as the number of events divided by the number of non-events. Stated another way, if the probability of an event is equal to P, or we'll call it P, then the odds ratio would be P divided by 1 minus P. So if we look on the slide here, you can see a 2 by 2 table. When we're looking at cell A, which is under D present, that's the disease, and next to E present, that means the exposure is present in these subjects. N equals 11. That's how many people were exposed to the problem that potentially caused the disease, and they also have the disease. When we look at B, in this situation, people were exposed to the problem or the situation, but they did not get the disease. When we go down to C, the disease is present in these people, but these people were not exposed. And to D, the disease is not present and the people were not exposed. So when we're looking at these numbers, our first cell is A, our second cell is B, our third cell is C, and our fourth cell is D. That's important when we're doing our calculations. Excuse me. Okay, so let's go back. When we look at this 2 by 2 table with cells A, B, C, and D, then the odds ratio is odds of the event in the exposure group, which is equal to A and B, divided by the odds of the event in the control or non-exposure group, which is C and D. Thus, the odds ratio is A divided by B together, which is divided by C divided by D. So A and B are divided, then that number is divided by the division of C divided by D. It's kind of hard to explain that without the formula, but you can see that up here. This is compared to the relative risk, which is equal to A divided by A plus B together, divided by C divided by C plus D. If the disease condition or event is rare, then the odds ratio and relative risk may be comparable. But the odds ratio will always overestimate the risk if the disease is more common. In such cases, the odds ratio should be avoided and the relative risk will be a more accurate estimation of risk. So the odds ratio can be interpreted as the number of times the event, in this case, let's say disease, will occur for every time it will not occur if the process were repeated many times. The ratio of two odds is called the odds ratio. Odds are not probabilities. However, they are very much related to them. High probabilities are associated with high odds, and low probabilities are associated with low odds. For events with very low probabilities, the odds are very close to the probability of the event. For example, a study observes the occurrence of total hip replacement in two groups. One was diagnosed with osteoporosis earlier, and the other was not diagnosed with osteoporosis. If the OR for the study is equal to 2 divided by 5, which is 0.4, it implies that the diagnosis of osteoporosis reduced the probability of total hip replacement by 0.4%. So the odds ratio is similar to the relative risk, but they're different, and is virtually equivalent to it when the prevalence of the disease is low. The odds ratio here is computed as you can see. Odds of disease given exposure divided by odds of disease given lack of exposure, which is equal to the odds of exposure given disease, odds of exposure given not disease. So the odds that a person was exposed given that they have the disease and the odds that a person was exposed given they don't have the disease can be computed in this way. Similar to the RR, it is a population parameter that needs to be estimated and interpreted with associations in terms of its value being below or equal to 1.0. An odds ratio that is greater than 1.0 means that the disease is higher among those exposed than unexposed. The opposite is true. If the odds ratio is less than 1, the odds of a disease is lower among exposed than unexposed. If the odds ratio is 1, the odds of disease is the same for both groups. You can think of the odds ratio as being a bit oversimplistic at describing real-world situations. If, for example, you have a positive OR, it doesn't necessarily mean that you have a statistically significant result. In order to figure that out, whether or not it's significant, you need to consider the confidence interval that you calculate and the p-values, if you know them, if you've determined them. The other issue is that even if you determine your results are statistically significant, that significance might not apply to all members of a population. There are nearly always a multitude of factors associated with risk. Okay, moving on to part 2, correlation and regression analysis. Certain types of studies may require that in addition to the variable associated with a disease or condition, the relationship and strength of that relationship might be known, or we want to know it. Correlation and regression analysis serve the purposes of quantifying that relationship. Correlation is used to denote associations between two quantitative variables, and regression can be used to summarize this association. We use correlation in everyday life to denote some form of association. For example, we might say that we have noticed a correlation between foggy days and attacks of wheezing. However, in statistical terms, we use correlation to denote association between two quantitative variables. We also assume that the association is linear, that one variable increases or decreases a fixed amount for a unit of increase or decrease in the other. As one goes up, the other goes up. As one goes down, the other goes down, etc. The other technique that is often used in these circumstances is regression, which involves estimating the best straight line to summarize that association. This table nicely represents how we use correlation versus regression and the meaning behind them. So when we're thinking about the meaning for correlation, correlation is a statistical measure which determines a co-relationship or association between two variables. Regression, on the other hand, describes how an independent variable is numerically related to the dependent variable. When we consider usage, how we're using these, in correlation, we use them to represent a linear relationship between two variables. We're not saying one causes the other. We're saying as one goes up, the other goes down, or vice versa. When we're using regression, we're using it to fit a best line and estimate one variable on the basis of the other. So it's a little different. Still not completely cause and effect. We have to do more analysis for that, but it makes more sense in that situation. When we're looking at the variables in correlation, we're not deciding if one's dependent or independent, but we are doing that in regression. We have an independent variable and we have a dependent variable. Correlation coefficient indicates the extent to which two variables move together, which direction and how much. Regression indicates the impact of a unit change in the known variable x, which would be the dependent, on the estimated variable y, which would be the independent. The objective of correlation is to find a numerical value expressing the relationship between variables. And the objective of the regression is to estimate values of random variable on the basis of the values of the fixed variable. So a little more on correlational analysis. When the regression equation is determined, the correlation coefficient, which we'll call R, predicts the nature and strength of the observed relationship. The value of R may vary from +1 to -1. If R equals 0, it implies that there's no relationship. The variables are not designated as dependent or independent. The two most popular correlation coefficients are Spearman's correlation coefficient, rho, and Pearson's product moment correlation. There are other correlations also like Kindle, and there are a lot of nice software packages that can help you calculate the correlation. But when calculating a correlation coefficient for ordinal data, select Spearman's technique. For interval or ratio data, use Pearson's technique. The value of a correlational coefficient can vary from -1 to +1, as it mentions in the slide here. While a +1 indicates a perfect positive correlation, a -1 indicates a perfect negative correlation. A correlation of 0 means that there is no relationship whatsoever. It doesn't necessarily mean there is none, but you can't find it from the data that you have. When there is a negative correlation between two variables, it means that the value of one variable increases as the other variable decreases, and vice versa. When there's a positive correlation between two variables, as one variable increases, the value of the other variable also increases. We also consider a standard error of a correlation coefficient. It's used to determine the confidence intervals around a true correlation of 0. If your correlation coefficient falls outside of this range, then it's significantly different than 0. The standard error can be calculated for interval or ratio type data, only for Pearson's product moment correlation, that is. The significance or probability of the correlation coefficient is determined from the t-statistic. We've talked about that in previous lectures. The probability of the t-statistic indicates whether the observed correlation coefficient occurred by chance if the true correlation is 0. In other words, it asks if the correlation is significantly different than 0. When the t-statistic is calculated for Spearman's rank difference correlation coefficient, there must be at least 30 cases before the t-distribution can be used to determine this probability. If there are fewer than 30 cases, you must refer to a special table to find the probability of the correlation coefficient, which you can find online or pretty much in any statistics handbook. So here are some graphs, scatter plots, that represent what we discussed in the previous slide. If we have a positive correlation, R is going to equal +1. +1 is a perfect correlation. This means that as one variable increases, the other also increases. So I could say, for example, as I increase my intensity of running, my heart rate increases at the same time. A negative correlation shows this type of graph. R is equal to -1. And maybe this means that the more I exercise when I'm resting, the less well, that's probably not a good example. But in this situation, what this means is that as one variable decreases, the other variable also decreases. And when we have 0 correlation, it means that we can't show a positive or negative correlation. It does not always indicate absence of relationship, but it can mean there is a relationship that's not linear. Okay, talking about regression analysis. Simple regression is used to examine the relationship between one dependent and one independent variable. It's widely used for prediction and forecasting. Where its use has substantial overlap with the field of machine learning. Regression analysis is also used to understand which among the independent variables are related to the dependent variable and to explore the forms of these relationships. In restricted circumstances, regression analysis can be used to infer cause and effect relationships between the independent and dependent variables. However, this can lead to illusions or false relationships, so caution is advised. Many techniques for carrying out regression analysis have been developed to deal with this issue. So when we're thinking of regression analysis, it goes beyond correlation by adding prediction. The regression line is a plot of the expected value of the dependent variable for all variables of the independent variable. It's going to be the one that best fits the data on the scatter plot. And there are 4 main types of regression. 1, linear regression. It involves one independent variable and the outcome variable, the dependent variable. This should be used to model a relationship between data if the dependent variable is continuous. A multiple regression involves 2 or more independent variables that are expected to influence the outcome variable, which is the dependent variable. A logistic regression would be used to model data if the dependent variable is dichotomous. And then we have nonlinear regression. It's used when a relationship between a numeric response and numeric explanatory variable or variables is nonlinear. In each case, analysis is performed to model any statistical relationship between the dependent and independent variables. So we'll talk about linear regression first, and it has the classic formula, y equals mx plus c, we usually put b there, plus the error term. This is useful for finding the relationship between 2 continuous variables. One is the predictor, or independent variable, which here is y, and the other is response, or dependent variable, which here is x. It looks for a statistical relationship, but not a deterministic relationship. So for example, we can say that people that live in a polluted area are more likely to have an asthma attack or experience wheezing, and therefore they would need more inhalers throughout the year. So our Y would be the pollution, our X would be the wheezing. And then we could switch it around, and the wheezing could be an indicator of the need for inhalers. We can use it two different ways there. Multiple regression means that we have our Y dependent variable, but we also have more than one independent variable. This is actually not correct. We need to switch this around. So still, Y here, that's okay. Yes, okay, I'm sorry. Please forgive me for that. I just looked at it differently. Okay, so here, Y is the dependent variable and X is the independent variable. So Y is going to be determined by X1, X2, and X3. And M indicates the influence of X. The error term here indicates how confidently the relationship can be predicted. The smaller the error term, the more certain one can be of the regression line. Moving to logistics regression. It's useful when the response variable is dichotomous. Here, we model the probability that the response variable takes on the level of interest as a function of the explanatory variables. Probabilities in logistic regression must lie between 0 and 1. Therefore, they will have to fit an S-curve or a sigmoidal curve instead of a straight line function as we did with linear regression. So in the case of one independent variable, we can fit the following model. You can see the equation here. Here, our pi of x is the probability that the response variable takes on the characteristic of interest. And x is the level of the numeric explanatory variable. Of interest, or what we want to know, is whether or not our beta is equal to 0. If beta is equal to 0, then the probability of success is independent of the level of x. However, if beta is greater than 0, then the probability of success increases as x increases. Conversely, if beta is less than 0, then the probability of success decreases as x increases. To test this hypothesis, the following test can be conducted based on estimates obtained from a statistical computer package, in which our null hypothesis would be beta is equal to 0, and our alternative hypothesis would be beta is not equal to 0. And we'll run through the calculations given the data and ultimately give us a p-value and an RR. In logistic regression, E to the exponent b is the change in the odds ratio of a success at levels of the explanatory variable 1 unit apart. So here's our formula. The odds of an event occurring is equal to what you can see there on the screen. So in this situation, an odds ratio greater than 1 implies that the probability of success is increasing as x increases. An odds ratio less than 1 implies that the probability of success is decreasing as x increases. Frequently, the odds ratio rather than the beta is reported in studies. So given this formula, when the ratio of the odds at x plus 1 to the odds at x, the odds ratio can be written independent of x, as you can see down here. So we'll talk a little bit about pharmacokinetics when we're trying to illustrate how to use nonlinear regression. In nonlinear regression, compartmental models are theorized to describe the fate, in this particular example, of a drug in the human body. Based on how many compartments are assumed, one or more, a mathematical model can be fit to describe the absorption and elimination of a drug. So in this situation, maybe phase 1 trial is to study the pharmacokinetic properties of a new drug, generally involving a restricted number of healthy volunteers. So for example, for a one-compartment model with first-order absorption and elimination, the plasma concentration at time t, or Cp, function of t, at single dose can be written as you can see there. Here, Ka is the absorption rate constant, F is the fraction of the D dose that is absorbed and reaches the bloodstream. Usually we're considering serum here when we talk about bloodstream. V is the volume of distribution, and Ke is the elimination rate constant. Ke can also be written as the ratio of clearance to volume of distribution. That is, Ke is equal to clearance divided by volume of distribution. In this situation, experimenters often wish to estimate an individual's pharmacokinetic parameters, such as Ka, V, and clearance, based on observed plasma concentration measurements at various points of time. So again, we're talking about nonlinear regression, but with the topic of pharmacodynamics. Pharmacodynamics estimates the dose, the response relationship between the dose of the drug and its therapeutic effect. The relationship between dose and effect is often, as we mentioned before, an S-shape or sigmoidal curve shape. S-shaped function that is approximately flat at low doses, no response. But then it takes on a linear trend from a dose that corresponds to approximately 20% of the maximum effect to a dose that yields 80% of maximum effect. Then it flattens out at higher doses. This gives us our S shape or sigmoidal shape. So a function of nonlinear regression is referred to as a sigmoid Emax relationship. And here's the calculation for that. In this situation, E is equal to effect. Emax is maximum effect attributable to the drug. C is drug concentration. And EC50 is equal to concentration producing an effect of 50% of Emax. N is the parameter that controls the shape of the response function. So let's consider application of regression analysis. It can be used for the following: model multiple independent variables, include continuous and categorical variables, use polynomial terms to model curvature, assess interaction terms to determine whether the effect of one independent variable depends on the value of another variable. So when we're thinking about regression analysis, it can unscramble very intricate problems where the variables are entangled like spaghetti. For example, imagine you are a researcher studying any of the following. Do socioeconomic status and race affect educational achievement? Do education and IQ affect earnings? Do exercise habits and diet affect weight? Are drinking coffee and smoking cigarettes related to mortality risk? Does a particular exercise intervention have an impact on bone density that is a distinct effect from another physical activity? All of these research questions have entwined independent variables and can influence the dependent variables. How do you untangle a web of related variables? Which variables are statistically significant and what role does each one play? Regression comes to the rescue because you can use it for all of these different scenarios, because you can use different types of data. So when you're using regression, always ask, does this relationship make sense? You still have to use your knowledge. Design additional experiments to test the regression relationship in the real world. It's critical to remember that correlation does not equal causation. Okay, moving on to part 3, multiplicity issues. So clinical trials often involve performing multiple comparisons. This leads to what we call a multiplicity problem. In this case, more statistical tests lead to higher likelihood of achieving statistical significance. It is highly likely to obtain a p-value below the level of significance, even when there is no true association. So think of it this way. If the level of significance is 0.05, which we usually like that, the probability of getting at least one statistical significance result is 64%. If 20 tests are done, that rises to 99.4% if 100 tests are done. So we learned before in previous webinars that the more numbers you have in regards to subjects or measurable variable factors, the more likely you're leading to this concept of normality, which is easier to find statistical significance in. So this is somewhat what it's talking about here. But you have to be careful with it. So these are guidelines on when statistical corrections are required to deal with the multiplicity problem and when these corrections are not necessary. Okay, so here, clinical trials that are free from this multiplicity issue have the following characteristics. There's only 2 treatment groups. They use one primary variable. They have a strategy to confirm the results using a single null hypothesis involving the primary variable, lacking interim analysis. This occurs when more than one independent statistical test is performed, and problems can also be introduced if there are many subgroups in a clinical trial. So multiplicity issues occur the more tests we perform, the more subgroups we have in our comparison activities. Multiple testing can be done without introducing false associations if certain statistical measures or corrections are applied. So for example, Bonferroni correction. This is known to be a conservative test and can lead to high rate of false negatives. It adjusts the significance level, which we call alpha here, by dividing the cutoff point, usually our favorite 0.05, by the number of independent tests being done. Oops, excuse me. Clinical trial adjustment can involve choosing a single primary endpoint. For example, a cold medicine might have desired endpoints of reducing congestion, lowering fever, and alleviating postnasal drip. Instead of determining if the drug has a statistical significant effect of all 3 symptoms, alleviating congestion could be made the primary endpoint for biostatistical calculations. And now we move on to our final part, part 4, survival analysis. Survival analysis is concerned with time to event data. In certain cases, the endpoint of interest is the time until the event occurs. The time to event or survival time can be measured in days, weeks, years, etc. Conventionally, or back in the day, it dealt with cancer death as the event in question, but it can handle any event occurring over any time frame, and this needs not to be always an adverse nature. Sometimes subjects may also leave the study prematurely. Such situations lead to censored observations as complete. When the outcome of a study is the time to an event, it is often not possible to wait until the event in question has happened to all subjects, for example, until they have passed on. Survival analysis can be distinguished from other statistical methods by censored data. They also make no assumption regarding normal distribution of time to event data. The event of interest may not occur during the study period. However, information from these subjects is available and is not discarded. There are several useful functions available that describe populations of survival time. The first is the survival function, as function of t. Here we call our random variable t, which is a randomly selected subject's survival time, and we can put it into this equation as written below. P is equal to t, p, the function of t greater than t, is the number of subjects in a population with t, the time, greater than the expected time, over the number of subjects in population. This function is assumed to be continuous, with s as a function of 0 is 1, and s as a function of infinity is 0. Another function that defines a survival distribution is the hazard function. Gamma is a function of t. The hazard function can be considered as an instantaneous failure rate at time t among subjects who have survived to that point, and it can be written as you see below. So in this session, we've covered relative risk, relative odds, correlation analysis, regression analysis, multiplicity issues, and survival analysis. Our takeaway points. Relative risk and odds ratio can be used to draw more accurate interpretations of research findings once we understand what they mean. Correlation lets us know the association or the absence of the relationship between variables, whereas regression predicts the value of the dependent variable based on the independent variable. Multiplicity refers to the potential inflation of type 1 error rate as a result of multiple testing. Example, due to multiple subgroup comparisons, comparisons across multiple treatments, etc. And survival analysis is used for analyzing data where the outcome variable is the time until the occurrence of an event of interest. And with that said, I want to thank you for your time and your attention.